When we talk about the first light in the universe, it is tempting to imagine a single dramatic moment, like someone flipping on a cosmic switch. But in modern cosmology, first light is not one event. It is a sequence. It depends on what you mean by light, what you mean by first, and what the universe was doing to that light at the time. The key idea is that the early universe was not empty space waiting to be illuminated. It was a hot, dense, expanding spacetime filled with matter, radiation, and the seeds of structure. Gravity was already shaping the future. Dark matter was already present, even though it does not emit light. Dark energy was already part of the energy budget in principle, even if it did not dominate yet. And the expansion of space was already stretching every wavelength it tried to travel. Right after the Big Bang, the universe was so hot that atoms could not exist. Photons were everywhere, but they could not go far. Any photon would scatter off free electrons almost immediately. So there was light, but it was trapped. It was like trying to see through a dense fog where the fog itself is glowing. In that phase, the universe behaved like an opaque plasma. We know this not because we can see it directly, but because the later universe carries a memory of it. The most famous memory is the cosmic microwave background, the CMB. That is not the first light ever created, but it is the oldest light we can observe directly today. As the universe expanded, it cooled. Expansion is not just galaxies moving through space. It is space itself stretching, described by the scale factor in general relativity. When space expands, radiation loses energy because its wavelength gets stretched. That cooling is why the universe eventually reached a temperature where electrons could bind to nuclei and form neutral atoms. This happened about 380,000 years after the Big Bang. The moment is called recombination, though it is really the first combination for most electrons. Once electrons were locked into atoms, photons stopped scattering so often. The universe became transparent. Those photons were finally free to travel long distances. That release is what we call the surface of last scattering. It is the first light, in the sense of the first light that could stream across the cosmos and still be seen today. The CMB is that light, cooled and reddened by 13.8 billion years of expansion into microwaves. It is astonishingly uniform, but not perfectly. It has temperature variations at the level of tens of microkelvin. Those tiny variations are not noise. They are the blueprint of structure. They tell us about the density ripples in the early universe. They tell us the universe is spatially very close to flat. They tell us the baryon density, the dark matter density, and the overall geometry. And they tell us that the primordial fluctuations were close to scale invariant and nearly Gaussian, which is strong evidence for an early period of accelerated expansion we call inflation. Inflation is not a proven fact in the same way the CMB is a measured fact, but inflation is the leading framework because it explains several observations at once. It explains why distant regions of the CMB look so similar in temperature. It explains why the universe looks flat. And it provides a mechanism for quantum fluctuations to be stretched to cosmic scales, becoming the seeds of galaxies. Now notice what is missing from that first observable light. There are no stars in the CMB, no galaxies, no planets. The universe at recombination was mostly hydrogen and helium, plus dark matter, plus radiation, with a tiny fraction of other ingredients. After recombination, the universe entered what we call the cosmic dark ages. This is a technical term. It does not mean the universe was empty or inactive. It means there were no bright sources like stars yet, so there was no visible starlight filling space. The only pervasive light field was the CMB itself, which by then had shifted from visible and infrared down toward microwaves as expansion continued. During the Dark Ages, gravity was quietly amplifying the density variations. Regions slightly denser than average pulled in more matter. Regions slightly less dense fell behind. This is gravitational instability. It is the engine of cosmic structure. Dark matter is crucial here. In the early universe, ordinary matter was coupled to radiation. Photons pushed back on baryons through scattering, creating pressure that resisted collapse. Dark matter did not feel that radiation pressure because it does not interact electromagnetically. So dark matter could start clumping earlier and more efficiently. It formed gravitational potential wells. After recombination, baryonic gas could finally fall into those wells without being dragged around by photons. That is why, in the standard picture, the first stars form inside dark matter halos. Dark matter does not make light, but it sets the stage for light to appear by shaping where gas collects and how fast it cools. So when people ask about the first light, I often separate it into two meanings. The first is the oldest light we can see, the CMB, released when the universe became transparent. The second is the first starlight, produced when the first generation of stars ignited. That second kind of first light happened much later, probably a few 100 million years after the Big Bang. The exact timing is still an active area of research because it depends on the physics of star formation in pristine gas, the abundance and clustering of dark matter halos, and feedback processes that can either trigger or suppress further star formation. The first stars were different from most stars today because the early universe had almost no elements heavier than helium. In astronomy, everything heavier than helium is called metals. Metals are efficient at radiating away energy, so they help gas cool and fragment into smaller clumps, leading to smaller stars. With no metals, primordial gas cools less efficiently. That tends to produce larger clumps and likely more massive stars. These are called population 3 stars. We have not observed an unambiguous population 3 star directly, so there is uncertainty in their typical masses and lifetimes, but the basic logic is solid. Cooling pathways in metal-free gas are limited, mainly through molecular hydrogen, and that changes how the gas collapses. When those first stars turned on, they emitted ultraviolet light. That light did something as important as shining. It changed the state of the universe. It started the epoch of reionization. Remember, after recombination, the universe was mostly neutral hydrogen. Ultraviolet photons from early stars and galaxies can ionize hydrogen by knocking electrons off atoms. Over time, ionized bubbles grew around sources and expanded into the intergalactic medium. Eventually, most of the hydrogen between galaxies became ionized again. That is reionization. It is not just a footnote. It affects how later galaxies form, because ionized gas is hotter and resists falling into small dark matter halos. It also affects what we can observe, because neutral hydrogen absorbs certain wavelengths strongly. How do we know reionization happened and roughly when? We have multiple lines of evidence. One is the CMB itself. Free electrons scatter CMB photons, and that scattering leaves a signature in the polarization pattern. From that, we infer an optical depth, which tells us the integrated amount of electron scattering along the line of sight, and therefore when reionization likely occurred in a broad sense. Another line of evidence comes from spectra of very distant quasars. Neutral hydrogen absorbs light at the Lyman alpha wavelength, creating a forest of absorption lines. At very high redshift, the absorption becomes nearly complete, indicating a higher neutral fraction. A third line of evidence comes from observing early galaxies directly with deep surveys, where we try to count how many ionizing photons they could plausibly produce. Each method has uncertainties, but together they point to reionization being largely complete by around 1 billion years after the Big Bang, with significant activity earlier. This is where cosmic expansion becomes more than a background detail. Expansion sets the clock and the distances. When I say a few 100 million years, that is cosmic time in an expanding universe described by the Friedmann equations. The expansion rate depends on what the universe contains: radiation, matter, and dark energy. Early on, radiation dominated. Then matter dominated. Much later, dark energy began to dominate. During the era of first stars, matter was the main driver of the expansion rate. That matters because the competition between expansion and gravity determines how quickly structures grow. Gravity tries to make overdense regions collapse. Expansion tries to pull everything apart, or more precisely, it sets the rate at which the background density drops and how hard it is for regions to decouple from the Hubble flow. In a matter-dominated universe, structure growth is efficient. In a dark energy-dominated universe, growth slows because accelerated expansion makes it harder for gravity to gather matter on large scales. So even though dark energy was not dominating when the first light from stars appeared, it still belongs in the story because it shapes the long-term fate of that light and the structures that produced it. Dark energy is the name we give to whatever is causing the cosmic expansion to accelerate today. In the simplest model, it is a cosmological constant, a constant energy density of the vacuum. In that model, the future is an ever more accelerated expansion. Galaxies outside our local group will recede faster and faster. Their light will be redshifted to longer wavelengths and eventually become undetectable. Star formation will decline as gas is used up or heated, and as galaxies become more isolated. The first light from the first stars, which once helped reionize the universe, will in the far future be stretched into radio wavelengths, diluted, and effectively lost in the darkness of an expanding spacetime. But I want to be careful with what we mean by lost. Photons still exist. They still travel along null geodesics in spacetime. But their energy decreases with the expansion, and the universe develops horizons in an accelerating phase. There are regions from which light emitted now will never reach us, no matter how long we wait, because space between us and those regions expands too quickly. That is a real geometric statement in general relativity. It means the observable universe is not the whole universe. It also means that the earliest light we can observe, like the CMB, is already a special boundary. We see it as a surface because we can only see back to the time when the universe became transparent. Earlier than that, photons could not travel freely. To probe earlier times, we need other messengers. This is where the phrase first light becomes even richer and also more constrained. If you mean the first electromagnetic light that could travel freely, that is the CMB. If you mean the first light produced by stars, that is the onset of cosmic dawn and reionization. But if you mean the first information from the universe, then light is not the only candidate. Neutrinos decoupled earlier than photons when the universe was about 1 second old. A cosmic neutrino background should exist, analogous to the CMB, but detecting it directly is far beyond current technology. Gravitational waves could also carry information from very early times, potentially from inflation itself, but again, the key word is could. We have detected gravitational waves from merging black holes and neutron stars, which confirms a major prediction of general relativity, but we have not yet detected a primordial gravitational wave background. Experiments search for it indirectly through patterns in CMB polarization, specifically so-called B modes. So far, we have upper limits, not a detection. That is an honest boundary of what we know. Let me connect this back to how we know what we know. The story of first light is not built from one observation. It is built from a network. The CMB gives us a snapshot of the universe at recombination and a precise set of cosmological parameters. Large-scale structure surveys show how galaxies are distributed today and how that distribution evolved, which tests the growth of structure and the role of dark matter and dark energy. Observations of distant supernovae reveal the accelerated expansion pointing to dark energy. Gravitational lensing maps mass directly, showing that most matter is dark and that it clumps in halos.